So we're going to do a few problems here that that involve thermodynamic cycles, and we're going to use the ideal gas law, and we're going to use the first law of thermodynamics to sort of analyze what's happening with energy and pressure and volume to a gas in this problem. And so in this one, we're going to start with 1 mole of an ideal of a monatomic ideal gas. Okay, it occupies 2 liters at a pressure of 10 to the 6th pascals. It then expands isobarically to a volume of 6 liters. It is then cooled isometrically until it is back to its original temperature. Finally, it is compressed isothermally back to its starting state. And so I just want to draw a picture of this. Might need a different marker. On a PV diagram. So here's a PV diagram, right? And so what we're saying is we're starting with some pressure here. And so here's our starting point. We'll say this is point 1, right? And this is 1 mole of ideal monatomic gas. We'll call this V1. Hopefully you can see that down there, V1, and that's 2 liters. So we'll call that V1, right? And this is at P1, so I'll erase that P. I'll put P1 here, and this is my pressure. And now it expands isobarically. Isobarically means at constant pressure, right? And so now it's out here at V2 equals, so it's 3V1. And so now it's here. That's what this is saying. It's saying it's expanding isobarically, so constant pressure, until it gets to 6 liters. And so I'm not putting the numbers in there as much as I can avoid it. And then it says it's then cooled isometrically until it's back to its original temperature. And so all that tells me is that it's cooled here until the temperature at this point is the same as the temperature at this point, right? And so notice that we have the number of moles, we have the volume, and we have the pressure at the starting point. And so we could determine what T is here, right? And so once we have this temperature, we have PV and T here, we have PV and T here, and then we know what all we know about this point is that it's got the same temperature at this point, and it's got 3 times the volume it does here, right? We don't know its pressure, but we can but we can figure out the pressure at this point because we know the temperature, the volume, and the number of moles, and so we can figure out what the pressure is here. And so then it's going to follow an isothermal line, right, back to its original state. And so this is what our gas has done. This is a thermodynamic cycle for this. And so, oops, this arrow goes the other way. Sorry, it goes this way, right? We move it isobarically, then isometrically, then isothermally, right, back to here. And so question 1, I haven't asked a question yet, is determine P, V, and T for each state. So we're going to determine PV and T here, PV and T here, PV and T here. Okay? We'll do that on the next. So what we want to do is calculate the pressure, volume, and temperature for each point in our cycle here. And so here's our pressure axis, here's our volume axis. This is our starting pressure, we call this P1, right? Here's our starting volume, we call it V1, and then over here is V2, which is 3V1. And so this is position 1, right? And since it's an isobaric process initially, it goes to here, which is position 2, right? Isobarically means constant volume, constant pressure, and then it comes down here until it gets to the temperature that it started with. We don't know what that is yet, but this is position 3. It's at the same volume. I didn't do that very well, but it's it's here somewhere, right? And then it follows an isotherm back up to the start, right? Something like that. That's not a straight line. That's an isothermal line. And so we're going to calculate the pressure, volume, and temperature at each one of these points, right? And we started with, this was 10 to the 6 pascals. I'll need to put the pascals in there because they're at the top. And so that was 10 to the 6th. And then step 2 is also 10 to the 6th for pressure, because the pressure didn't change. And then we said the initial volume, V1, was 2 times 10 to the minus 3. That is to say it was 3 liters. It's 2 liters, sorry. And then it expanded to 3 times its original volume, or 6 times 10 to the minus 3 liters. And then getting back to here, so that puts us here. This guy's volume is the same, right? 3 also has 6 times 10 to the minus 3 liters. So this guy went up to 3 times the volume, and then this is a constant. This is an isometric problem, or an isochoric problem, or a constant volume problem. And so now we've got to figure out what the rest of these are. And we know a few things. We know that P1 V1 is equal to NR T1, right? And so we could determine T1, which is P1 V1 over NR. And so that's 10 to the 6th pascals times 2 times 10 to the minus 3 cubic meters divided by 1 mole times 8.314 joules per mole Kelvin, right? And that gives me a T1, which is about 240, if you calculate that out. 240, one more time, 240 Kelvin. For some reason I'm having trouble with that, 240. And now we can kind of get the rest of these by saying, look, since P1 V1 is equal to NR T1, we know that P1 V1 over T1 is a constant. And that means P1 V1 over T1 is equal to P2 V2 over T2, or P3 V3 over T3. And so if we look at these two equations, these two guys have the same pressure, right, for here. And so this just, since these two guys have the same pressure, V1 over T1 is equal to V2 over T2. Right? And since V2 is 3 times as big as V1, that means T2 has to be 3 times as big as T1 for this equation to remain true. In other words, T2 is equal to V2 over V1 times T1 if we arrange this. And so it means it's 3 T1, or this is 720 Kelvin. Right. And so now, since the problem tells us that the temperature goes down until it reaches back to the original temperature, we know that this is also 240 Kelvin, right? What we said was it's compressed and it's cooled until its temperature reaches the temperature that it started at, right? And so until T3 equals T1. And so now we've done this, and so we can go back to this equation. We can say, well, P1 V1 over T1 is equal to P3 V3 over T3. And since the two temperatures are the same, we know that P1 V1 is equal to P3 V3, or P3 is equal to P1 times V1 over V3, right? This is just P1 over 3, which is just 3.3 times 10 to the 5th pascals. And so those are all my pressure volumes and temperatures for all the points on my chart. So now we're going to ask another question of this. I'm going to erase all this work since we've filled out our chart with our pressure volumes and temperatures. And so my gas is going through this cycle like this, through a complete cycle. And we're going to say determine the change in E internal and Q and the work by for each process. So when it goes from 1 to 2, what's the change in internal energy? What's the Q in? I'll put a Q in there. What's the work by? Same thing for 2 to 3, same thing for 3 to 4. And so we'll say change in E internal in joules, Q in joules, work by in joules. And this is for 1 to 2, 2 to 3, and 3 to 1 for each of these processes, right? And so there are a few of these we know right away. For example, you should be able to tell me just off the top of your head, what's the work done by the gas going from 2 to 3? Right? You remember the work by is equal to the integral of P dV. There's no dV, the volume doesn't change, and so the work by going from 2 to 3 is 0. Furthermore, the change in E internal is equal to CV, that's the heat capacity at constant volume, times the change in the temperature. We established that already also. And so if I look for 3 to 1, we already said in the problem this was isothermal. So there can be no temperature change between these 2 points because it's on an isotherm, and so the temperature stays constant along there. And so that means the change in the internal for 3 to 1 is also 0. And so that gives us a little help, and then we can just start evaluating these. So for example, I can say, let's calculate the work done by the gas going from 1 to 2, right? Work by going from 1 to 2 is equal to the integral of P dV. And so the pressure is constant, and so that's P times the integral from 1 to 2 of dV, right? And that's equal to 10 to the 6 pascals times the change in volume going from 1 to 2, which is equal to 10 to the 6 pascals times 6 times 10 to the minus 3 meters cubed minus 2 times 10 to the minus 3 meters cubed. This comes out to about 4,000 joules. And so that's this guy. 4,000 joules. Right? We could look at that same process and calculate the change in internal energy. Right? So the change in internal energy going from 1 to 2 is just the heat capacity at constant volume. Even though it's not a constant volume process, the change in internal energy is the heat capacity at constant volume times the change in temperature for any process. And so that's just 3/2 NR. The 3/2 is because we said in the first part of the problem that this is a monatomic gas. If it was diatomic, we'd have like 5 halves there. Times the temperature difference going from 1 to 2, so it's 720 Kelvin minus 240 Kelvin. And so this is 3/2 times 1 mole times 8.314 joules per mole Kelvin times 480 Kelvin. And so if I evaluate that, that's a 1.5 times 8.314 times 480. That's about 6,000. About 6,000 joules, and so that goes here. Well, we know from the first law that change in E internal is equal to Qn minus work by, or Qn is equal to change in E internal plus the work by. And so for this one, that means Qn 1 to 2 is 6,000 joules plus 4,000 joules, or 10,000 joules. I don't need the joules on here because I put them at the tops of the columns. Okay, and so right away I can tell you that that this one is now minus 6,000, because if I add up the changes in internal energy in the gas or on any closed loop, I have to get back to where I started with. And so the total change going from 1 and all the way back to 1 has to be 0. And so this plus this plus this has to be 0. And so that's got to be minus 6,000. And so let's just check it using the same formula. Right, we're going to say change in E internal going from 2 to 3 is equal to 3/2 NR. That's what this guy is, times, going from 2 to 3, it's 240 Kelvin. You can probably already see it now, minus 720 Kelvin. And so it's equal to 3/2 times 1.0 moles times 8.314 joules per mole Kelvin times 480 minus 480 Kelvin, and you get minus 6,000 joules, which is exactly what we expected at that spot. That means this also has to be minus 6,000 joules, right? Because our first law, change in E internal, equals Qn plus minus work by. And so for this process, that is equal to that minus that. Since that's 0, these two guys have got to be the same. So let's do these guys. We have a formula for this guy, right? So work by going from 1 to 3 is the integral of P dV, right? And since it's an isothermal process, 3 to 1, right, then we can use PV equals nRT, or P equals nRT over V. You can see by following this curve that the pressure is changing in this process, and so I can't just pull the P out like I could for an isobaric process. So I've got to figure out some way to be able to do this integral, and the way I do it is I use the ideal gas equation. N, R, and T are all constants. This is an isotherm, the T is a constant. And now the one that changes here is the same as my integration variable. And so this gives me nRT, I can pull them outside the integral, going from step 3 to step 1 of dV over V. And that's equal to nRT times a log of V, evaluated from 3 to 1. And so that's equal to nRT times the log of V1 minus the log of V3, right? And that's equal to nRT times the log of V1 over V3. And so if I'll just do that over here, right? And so the work by going from 1 to 3 is 1.0 moles times 8.314 joules per mole Kelvin times, so the T, I didn't specify whether it was 1 or 3 because it doesn't matter. 1 and 3 are at the same temperature, and so I'll just say 240 Kelvin times the log of 1/3. And so if I evaluate that, I get minus 2200 joules. And so that was going to go here, minus 2200 joules. Notice the work by here is negative because the gas is being compressed. The gas is getting smaller, so work is being done on the gas, unlike when I'm going from here to here where the gas is moving in positive direction in V and the gas is expanding. Here it's being compressed, and so the gas is doing negative work, or work is being done on the gas here. And so now I can go back to my first law, and I can say change in internal energy, this is for 3 to 1, is equal to Qn minus the work by. And so since this guy is 0, it means these two guys are equal. This is minus 2200 joules. So there are a few things to learn from this. First of all, the useful numbers from this are so lots of things operate on these cycles, but engines are gas-powered engines are typically described by some kind of PV diagram cycle. And so what that says is that in this complete cycle, the engine does 4,000 joules of work, say, and has 2,200 joules of work done on it. And so the net work done is 1,800 joules. In order to make that happen, I needed 10,000 joules of heat to go in to get that 1,800 joules to come out. Now I lost heat out here, but this is the kind of thing that, you know, when your engine heats up your engine block and stirs the air, you can't run away from this stuff. So the important numbers here are the amount of heat that you require to go in. This is the engine that came out of, say, your gasoline, 10,000 joules of energy to get 1,800 joules, net joules of work. And so we would say the efficiency is E equals the net work, so just the total of this, divided by the heat I had to put in. That's the combustion energy in my gasoline, times 100%. In this case, E is equal to 1,800 over 10,000 times 100%, or about 18%. That's a pretty reasonable number for an engine. And what we'll find later on is that you can't get away from these negative numbers. You'll never get in fact, the most efficient engines you can get are typically around the 20 or 30% or something like that. A couple other things to notice. So let me grab a different color marker here really quick. So this the work by on the first cycle was the area of this. That was this number, right? To calculate this number, we used the pressure times d volume, which is this, and so it's P times delta V. Similarly, when we calculated this value, we took the area under the curve here, this area, under the isothermal curve. And so This number, I don't have a third color. This number here, the net, is the difference between these two. It's this number. And so the net work done in a thermodynamic cycle is the area enclosed in the cycle. Sometimes that's easy to calculate, but what we did here is we just took the difference of the block and then what was under this guy, and the difference between those two gave us the area inside the arc, inside the cycle, and that's the work done. Well, I can't do that very well. I'll try one more. These things are always running in the clockwise direction. You're always running an engine this way, so that the goal of any engine is convert heat drawn in, which usually is due to some combustion process in a gas or diesel engine, some burning process. That's the heat that's drawn in, and converting it into mechanical work. And the curve on a PV diagram delineates or marks out the work done.